Last time we met, we saw how a quadcopter stays airborne by balancing the forces of four spinning propellers. But if you take a drone and pause it mid-flight, frozen completely still in the air, you quickly realize something important. Those spinning pieces of plastic and woven carbon fiber are just raw hardware. On their own, they have no idea how to actually fly. They need a steady stream of power and specific instructions to defy gravity. Take a look at this exploded view image from our flight manual. It pulls the internal electronics apart so we can see every single component. While it looks like a mess of wires, it helps to view this robotic system like a living animal. If we think of this drone as a mechanical creature, we can map these complex engineering terms onto parts of a body you already know. By learning its anatomy, we can figure out how it manages to stay in the sky. Every animal needs bones, so we'll start with the drone's skeleton. That's the frame, typically shaped like an X and made out of woven carbon fiber. This animated diagram compares two types of frames to show a major physical challenge. The frame on the left is perfectly rigid, which is exactly what we want. If the skeleton wiggles or bends under the heavy downward stress of flying, like the frame on the right, the drone loses balance and fails entirely. But that rigid frame also has to be incredibly light, or gravity will simply pull it back to the dirt. Look at our technical image. Underneath the skeleton is the lipo battery, the stomach of our animal. Standard batteries can't feed it fast enough. The lipo dumps massive electrical fuel instantly, providing the sudden burst of energy needed for liftoff. But a strong set of bones and a stomach full of electrical food still won't get us airborne. That energy is totally useless until we give the body a way to flex. Follow the wiring in our diagram to the ends of the arms. Here are the electronic speed controllers and brushless motors. These act as heavy-duty muscles, taking raw energy from the stomach to physically push air and create lift. Notice this motor's cross-section has no physical gears. Electrical pulses in the outer copper coils create flashing magnetic fields, pulling the center magnets in a frictionless circle. This spins the propellers at blistering speeds, forcing air downward to push the machine up. However, having strong muscles is dangerous without direction. If all four motors drank raw power from the battery and spun as fast as they could, the drone would immediately flip over and crash. To fix that, we travel to the very center of our technical drawing. Resting right in the middle of the skeleton is a tiny, flat circuit board. This is the flight controller, the central nervous system of the operation. It dictates every single micro-movement. Attached to it is a small antenna called the radio receiver. These are the drone's ears. When you press forward on your joystick, you're beaming an invisible radio wave into the sky. The ears catch that signal and instantly pass your request down to the brain. This diagram shows what the brain does with your command. It receives your single instruction to fly forward, calculates the physical math required, and divides that request into four separate commands. It then sends those custom commands to the individual muscles. The pilot tells the drone where to go, but the silicone brain actually figures out how to get there. It's the ultimate safety net, ensuring heavy electrical bursts become smooth, stable flight instead of chaos. So let's finally end this mid-air time freeze and snap our mechanical animal back together into one unified flying machine. The ears hear the command, the stomach delivers the fuel, the brain does the math, and the muscles fire. The propellers spin up to thousands of revolutions per minute, and the drone rockets up from the launch pad. Suddenly, a massive gust of wind hits the side of the skeleton, trying to tip it over. But the drone doesn't crash. It seamlessly adjusts its balance and holds its position in the air, perfectly level. A human pilot simply cannot react fast enough to do that manually with a joystick. To survive that gust of wind, the drone's onboard brain had to fight the physical pull of gravity by recalculating its balance thousands of times in a single second. Now that we know the anatomy of the machine, we need to understand how it actually thinks. Next time, we'll slow down a vertical takeoff to the exact microsecond and watch that silicon brain do its math in real time.